Okay, so this is the integral that we want, and this is the info we might need. The very first thing that we do is we let x equal something else with a different variable. We need a trig substitution. So these are pretty much the only three you're likely to see. Now let's make a comparison. Does this here look more like this, or that? It may not be a perfect match, but which one does it look most like? I propose that our problem looks most like this because it has a square root, but this one has the variable minus the constant. This is the constant minus the variable, which is what we have. So for that reason, we're going to sort of be looking up here instead of at these two there. So we need x to equal something. Here is what we're going to let it equal. So we should use 4 sine, and just pick a variable other than x. How about like theta or u? How about just theta, okay? Now let me show you how I got this. So it's going to be x equals, I got 4 because it's the square root of that. So if this was like 49, that would have been 7. That was 81, that would have been 9. And the reason I got sine is because I'm going to use this function. I know it's inverse, but when you do the substitution, it's just sine. So for instance, what if the problem that you had in your homework looked more like this? If it looked more like that, then instead of sine, it would have been secant. What if what you have looked more like this? Then you would have used tangent there instead of sine. And again, 4 is just the square root of this. Okay? So that's how I made that substitution. That is the key step. Everything depends on this being correct. So we're going to have to rewrite all of this in terms of thetas or whatever other letter you would have chosen. But notice that this is x squared and this is just x. So we're probably going to need x squared. So we can just quickly square both sides, right? If you square that, boom. If you square that, boom. Now, as soon as you have x, you need dx. So dx is the derivative. So derivative, now the derivative of 4 sine theta is 4 cosine theta d theta. I propose that we're now ready to write this in terms of all thetas. Cosine theta d theta. And so this equals that. And let's see. So now maybe we can take the 16 times the 4 and call it 64 in the front. And inside we're left with sine squared theta over square root like this here. Now let's see here. So what about this? What if I factor out a 16 from the bottom? So watch, I took out a 16 from the two terms in the bottom and I put that out to the front because the square root of 16 is just 4. Now 64 over 4 is just 16. Now in here, 1 minus sine squared, what is that? Remember how sine squared plus cosine squared equals 1? Well, if you subtract the sine squared to the other side, it'll be 1 minus sine squared. But that, of course, would be left equal to cosine squared. And that's how I change 1 minus sine squared into cosine squared. And that's good because the square root of cosine squared is just cosine, and it knocks out cosine upstairs. So here's what we're left with. So the problem simplifies to this here. This equals everything above it. So this is better, but now look, there's a power of 2. I don't want to integrate a power of 2, so we're going to use this, what they call the power reduction formula. So instead of sine squared theta, we're going to turn it into that. Okay, so that turned into this here. Everything else stayed the same. Maybe we can kick out the 1/2 to the front. So that turned into 8 in the front. And you know what? Now I think we're ready to take the actual antiderivative. So let's keep the 8 in the front. And now instead of the integral, it's gone because we're going to take the antiderivative. The antiderivative of 1 would just be theta because the derivative of theta is 1 minus. Now here, watch. The antiderivative of cosine 2 theta, there's going to be a sine 2 theta in there, but there's going to be more than that because if you take the derivative of sine 2 theta, watch. The derivative of sine 2 theta would be cosine 2 theta times 2, right? Because it's the chain rule. But this doesn't have a 2 in the front. So I'm going to have to put a 1/2 right there. Because if I take the derivative of that, when the derivative of 2 theta gives me a 2, that 2 knocks out the 1/2. So it's just regular cosine. So that's just a little chain rule action there. And if you want, you can put your plus C. And now why don't we distribute the 8? Now, look, here, the 2 is a problem. So instead of sine 2 theta, maybe we can use that double angle and turn that into 2 sine cosine for just that part there. Okay, so we have 8 theta minus, so sine 2 theta become 2 sine cosine. Maybe we can just call that 8 right there. Now watch, let's go back to the very first part that we did. You know how the very first thing we did was to say x equals 4 sine theta. What if we try to get theta by itself? Let me divide the 4 underneath the x, so I have this here. Let me just reverse the order of that equation. And now what if I do this? What if I take the sine inverse of both sides? Why would I do that? Because sine inverse knocks out sine, and it exposes theta. And so theta equals sine inverse of x over 4. And that's good because now here you see all these thetas. All of those thetas can now become sine inverse x over 4. So that theta, they all became sine inverses. Now that just pretty much stays. We're going to deal with that in a moment. Here, this one's kind of cool because sine and sine inverse knock out. So it's just 8 times x over 4. The 8 times the x over 4 gave me 2x. This part here is what we need to take a timeout and discuss here, perhaps on this green paper. So let's jot this down over here. Remember that sine inverse gives an angle theta, such that sine of theta is that thingy there. So watch what I do. Anytime I have sine inverse, so I'm going to let sine inverse, anything trig inverse is an angle. So I'm only looking in here. So I'm going to let sine inverse of whatever that says, let it equal just some number u or some angle u. Okay, so u is an angle. If you want, just call it theta 1, whatever, just so it's not the same as the theta that we've been using. Now watch what I do. Let me take the sine of both sides. So if I take the sine here and the sine there, these would knock out. And it's just x over 4 equals sine of theta 1. Now here's what we can do. We can actually make a picture where the angle is theta 1. So we have that sine of theta 1 equals x over 4. But remember that sine, if you think of SOHCAHTOA, sine is opposite over hypotenuse. So this here, this would be your opposite over your hypotenuse. So theta 1 is there, and from this position, sine is x over 4, where x is the opposite, and the hypotenuse is 4. And we don't know what this is, but we can go to middle school and do the Pythagorean Theorem. A squared plus b squared equals c squared. So that question mark squared plus x squared equals 4 squared. And so question mark squared equals 16 minus x squared. And so question mark equals that if you square root both sides. So this missing piece is that here. How come this picture is helpful? Because now we can go back to the original part. Remember that sine inverse of x over 4 was allowed to be set equal to theta 1. So by substitution, all of that is just theta 1. And that's good because now we can go cosine of theta 1, where theta 1 is right there. And cosine is, SOHCAHTOA says that cosine is adjacent over hypotenuse, where this is your adjacent and this is your hypotenuse. So cosine of theta 1 would equal that over 4. So anytime you run into a situation like this, that inner inverse part, let it equal some random angle. And then take the whatever of both sides. In this case, we took the sine of both sides. And that statement there, that gave us a picture. Once the picture is completed with Pythagorean, we can go to the original thing and go that function of whatever angle you decided to call it. And that'll give you some other expression. So going back to the main problem, that gets replaced by this thingy right there. And then instead of sine inverse, you can just call it arc sine. It's the same thing, it's just a different notation. That got simplified a little bit. So I propose that this is the final result.